Okay, hi everybody. Today we're going to be recording our fourth vector session because I wasn't able to live stream it this time. And instead of having all these technical difficulties and wasting all this time trying to figure this out, I'm just going to record it and then I'm going to post it in the pins of the Math AA channel. And then you guys will be able to see it. If you have any questions, of course, just DM me and I will help you out. And I will also post the notes so you can go along with me as I do them. So, yeah, I guess let's begin. So the concept we're going to be covering for this session is systems of equations and vector equations in 3D. So for systems of equations, we're going to look at row reduction, which is this algebraic version, like twist on elimination, which you guys already know. And then technology, which is using a calculator to solve it. And then we have vector equations in 3D, which will focus on lines in 3 dimensions, how the 3D Cartesian plane works, X, Y, Z, stuff like that, closest distance, intersections, all that fun stuff. So let's start with systems of equations. So we're going to introduce the methods first. So yeah, I solved this one already here. And it's a very simple system. All you have to do is use elimination. Add the first one here to the second one, and you get 0 for the y. 5x equals 20. Divide both sides by 5. X equals 4. And then you solve for y in the above equation. And then after that, you have 4, 1. Meaning x equals 4, y equals 1. Let's do this next one, shall we? So, it seems that in order to eliminate this x, we have to do 2 times this plus the bottom. That gives us 0 plus 0 equals negative 4. You're probably thinking that looks wrong. Well, in a way, it is. 0 can equal negative 4, which means there are no solutions. Thus, here's how we show that. Curly brackets and a little circle with a line through it. So let's do the next one. Seems like we can use the same method as before. Times 2 plus the bottom. So it gives us 0. Plus 0 equals 0. Okay. So that means 0 equals 0. And that means that there are infinitely many solutions. This means that there are infinitely many x values or y values that can satisfy this equation. So if we let x equal t, our system becomes negative 2t plus 4y equals 1, and then x equals t. Hang on. I have 2x. And then when x equals t, we can solve this one and plug in t. So y, therefore, equals 1 over 4 plus 1 over 2t. And the way we can show this is by doing the coordinate thing as last time. So t is our x, and then 1 over 2t plus 1 over 4 is our y. There she is. So now that we looked over these, we're going to try something called row reduction. Now here are the steps to row reduction. Step 1 is convert to matrix, which means we want to turn this over here into a matrix. That looks like that. Step 2 do row operations to cancel a variable. Then 3, convert back to a system. Solve, easy peasy. So, those are our steps to row reduction. And we're going to try this out. Okay, so step 1 is converting to a matrix. Now, what are the components to a matrix? Well, a matrix has rows and columns. Rows represent the number of equations, and the columns represent number of variables. So therefore, for this one, we'll have 2 rows, because there's 2 equations, and then for an augmented matrix, which is what this is called, we're going to have 2 columns for the variables, plus 1 column, which represents the equals. So this is what it would look like. Turning it into an augmented matrix, we have 2, 3, because this is the variable column representing x. Then we have 1, -1, since that's a variable column representing y. Then we add a line. This represents the equals. That's the equals. So, yeah. So now we put what's on the other side, the equals. So 9 and 11, and that's the equals column. So here's our matrix, right? Our augmented matrix. So what are we going to do with this? Well, we're going to move on to step 2, which is do row operations until we turn this part here into 0. So let's think about this. What can we do with the second row and the first row to turn this 3 into 0? Well, I'll tell you. We can take the second row and multiply it by 2 and subtract 3 times the first row. So Rn represents the nth row. So because the common denominator in this is 6, so if we multiply both by 6 and subtract them, they cancel. So if we do 2 times row 2 minus 3 times row 1, we're only doing this to row 2. So row 1 stays the same. So 2, 1, 9. But then the second row, well, 2 times 3 is 6, and then minus 3 times 2 is 0. 2 times 1 is -1. 2 times -1 is -2. And then subtract 3 times the first row is going to be -2 minus 2, which is -5. And then for the last part, we have 22 minus 27, which is -5. So we can cancel the negatives here because that's 0. And then when we convert back into a system, which is step 3, we're going to have 2x plus y equal 9. And then we're going to have 5y equal to 5. So from here, we know that y equals 1. And then when we plug it into this equation, we have x equals 4. So it's the same solution as before because it's the same equation. So we state it the same way. So 4, 1, curly brackets. Now let's do this part. This is the same one as before, the one that had no solutions. So our first step is to convert it into a matrix. So like what we did before. So -1, 2, representing the column for x. Then we have 2, -4 for the y column. Then we have an equal sign being a line. Then we have 0 and -4. That's our matrix. Then we want to do row operations to turn this part into 0. Well, how do we do that? It's pretty simple. One second. So we can do the same thing as we did before, and then we can take the second row, and then we can add it 2 times the first row. What does that do? Well, it doesn't change the first row, that's for sure. But the second row, well, 2 plus 2 times -1 is 0. -4 plus 2 times 2 is -4 plus 4, which is also 0. And then -4 plus 2 times 0 is -4. So this is what it looks like when there's no solutions. Converting it back to a system will look like this. -x plus 2y equals 0. And then we have 0 equal to -4. Now, 0 can't be -4. Therefore, no solutions, as we did before with the curly brackets and a circle with a line going through it. Now we're going to do... Sorry. Oh, okay. Now we're going to do row reduction with this guy. Same thing as always. Step 1, matrix. -2, 4, 4, -8, 1, -2. What row operation can get this part to 0? We have R2 plus 2R1. So same thing as before, right? So that turns our matrix into, first row doesn't change. Second row does though, so 0, also 0. And then, let's see, -2 plus 2 times 1 is -2 plus 2, which is 0. So the whole entire bottom row is 0. So turning it back into a system, we have -2x plus 4y equal 1, and then we have 0 equals 0. Infinitely many solutions, right? So let's let x equal t. Therefore, y equals 1 over 2t plus 1 over 4 from plugging it into this equation. So thus, our solution to this thing is the following. So t 1 over 2t plus a fourth. That's our solution. So that was row reduction. And now we're going to use our calculator to solve these using something called RREF. Now, what does RREF stand for? It stands for row reduced echelon form. So let me give you a little rundown of what this does. So let's say we have augmented matrix A, B, C, D equals EF. In our calculator, what RREF does is it makes it so that we have 1, 0, 0, 1 equals S1, S2. Now, the S's stand for solutions. So if we convert this back into a system, we have x equals S1, y equals S2. So effectively, this RREF solves a system for you using some automatic row operations. So it's the row reduction stuff we looked at, but with a little more to it. So in a university linear algebra class, you would actually learn how to do this by hand. But we're not going to look into that, because that's not part of AHL. So another way that a calculator could show a matrix is like this, with square brackets. So A, B, C, D, E, F. And that's okay, because both are the same. Both are the same. So that's a quick rundown of how REF works. And I'll actually post a video or link a video to how to do row reduced echelon form on your TI-84 calculator. And for those of you who have TI Nspire models, there is actually a much easier method to doing this. And all you have to do is use your little keyboard to type RREF with a bracket, with a left bracket, and then we can plug in a matrix from the option menu, and then we can press equals, and that gives you the answer. So it's a little more complicated on the TI-84, so I'll post a video from someone on how to do that, and you guys should understand. So right now, I'll go through this as if you know how to do this. So if you don't, please pause this and go watch the video that I posted as well. So yeah, let's do this. So step one is converting this into a matrix, right? So we're going to do that. So 2, 1, 3, -1, 9, 11. So now, on paper 2, if they ask you to do this, you would put an arrow with RREF, plug this into your calculator, and you'd get 1, 0, 0, 1, 4, 1. Now, if you convert this back into a system, this just means that x equals 4 and y equals 1. So if you want to turn this into a solution, that's the same as saying 4, 1. Okay, let's do it to this guy. So step 1, turn to a matrix. So -1, 2, 2, -4, 0, -4. Okay, so arrow RREF equals, let's see, 1, -2, 0, 0, 0, 1. So, turning it back into a system, we have x minus 2y equals 0, and then we have 0 equal 1. 0 doesn't equal 1, therefore, no solutions. Okay, oh crap, okay, wait. Sorry about that. Since we have some extra space here, we can do it sideways. So convert to a matrix is step 1. And then if we do our RREF, you can do it sideways as well. We have our thing being equal to this stuff. So it would be 1, -2, -1/2, 0, 0, 0. Okay, so turning it back into a system, it means that x minus 2y is -1/2, and 0 equals 0. So when 0 equals 0, you can have infinite solutions for x or y, so you can make x equal to t. Always put let. So plugging it into y, we have y equals 1/2, t plus 1/4. Okay, so in our little solution thing, we're going to have t 1/2 t plus 1/4. And there we go. That's how to do that one. Moving on, we have some more super fun stuff. So looking at question 4, use row reduction to solve the systems of equations in part A, then use your calculator to solve the rest. So A is using row reduction. So we're going to quickly do that. So let's convert it into a matrix, which is... So the difference here is that we have 3 equations this time. So therefore, we have 3 rows, since rows signify the number of equations. So there's going to be 3. And there's also 3 variables. So there's going to be 3 variable columns and then an equals column. So that's 4 columns in total. Okay. So 2, 1, 3 is the x column. 1, -2, 5 is the y column. And then -1, 3, -1 is the z column. And then we have 2, 7, 0. Now, using row reduction, what we want to do if we have 3 equations is to get this part here is to 0. So the first part we start with is here, and then we do here and then here, or 2 of those at the same time. So we're going to start by, let's see, what can we do with the second and third row to get the bottom 3 to a 0? Well, we can take row 3 and subtract 3 times row 2. Easy. So the first row doesn't change. 2, 1, -1, 2. Then the second row also doesn't change. So 1, -2, 3, 7. But the third row changes. So 3 minus 3 times 1 is 0. 5 minus 3 times -2 is going to be 5 plus 6, which is 11. Yeah. And then we have -1 minus 9, so -10. Then we have our boy 0 minus 3 times 7, so -21. Now we want to turn the thing above it to a 0, so the 1. Let's do the 1. So, if we take 2 times row 2 and subtract row 1, that would give us 0 for the 1. So let's do that. First row doesn't change, once again. 2, 1, -1, 2. Second row does change. So 2 minus 2 is 0, 0. And then -4 minus 1 is -5. 6 plus 1 is 7. And then we have, let's see, 14 minus 2, which is 12. Then we have 11, -10, -21. Okay. So the common denominator between these two guys is 55. That's not very fun. But the common denominator between these two guys is 11. So we're going to do that one instead. So what we're going to do is we're going to take row 3 and subtract 11 times row 1. Okay? Okay. So first row doesn't change. 2, 1, -1, 2. The second row also doesn't change, so 0, -5, 7, 12. Third row changes. Okay, wait. I'm really sorry. Please disregard everything I said because you can't use the first row. I made a mistake, and this is something to learn from. If we used row 1 to subtract from row 3, this would no longer be 0. This would be -2. Or no, this would be -22 because this has to be 0, right? So this changes that to not 0. So that's why we can't use row 1. So unfortunately, we're going to have to use our common denominator, 55, to do this. So if we're using only the second and third row, we have row 3. We're going to have to multiply both by a common factor. So 5 times row 3 plus 11 times row 2. This is going to have some annoying numbers, but we can still do this, guys. So first row doesn't change. 2, 1, negative 1, 2. Second row doesn't change. 0, negative 5, 7, 12. Third row changes. So this is still 0 because, yeah. And then this is also 0 now. Negative 10, so negative 50 plus 77 is 27. Yeah. And then what's negative 21 times? So negative 105 plus 132, I think. That gives us 27 again. So this is fun. So now that these parts are 0, we can turn this back into a system. 2x plus y minus z equals 2. Negative 5y plus 7z. I wrote z by accident. So 7z equals 12. And then finally, we have 27z equals 27. God, I keep putting... Okay, so judging by the bottom one, z equals 1. Then plugging that into the second lowest equation, we have, let's see. Y equals negative 1. Because if you have z equals 1, 12 minus 7 is 5, so negative 5 equals 5. So you have to multiply that by negative 1 to give you 5. And then plugging both of those values into the bottom equation, sorry, this is really confusing, we have 2x minus 1 equals 2. So x equals 2. Because we have to, from 4, which is 2 times 2, we have to subtract 1 twice to get back to 2. So in order to show this as a solution, we have x, y, z. Okay. So now we're going to use our calculator to do the rest because this is really annoying. This takes a lot of time. So from here, we're going to be like, yeah, we're just going to use our REF. So as you can tell, this one has 2 equations. Yeah, 2 equations and 4 columns. So our matrix would look like this. 1, 2, 2, 3, 3, 1, 6, 7. Now on our calculator, if we do R, R, E, F, let me just really quickly do that. I'll let you guys do that too. So R, R, E, F, matrix, 2, 4, 1, 2, 3, 6, 3, 1, 7. We have the following. We have 1, 0, negative 7. That looks like a 10. Negative 4. Then we have 0, 1, 5, 5. So turning it into a system, we have x minus 7, God, okay, 7z equals negative 4. Then we have y plus 5z equals 5. So if you think about it, if we had our this matrix as a 3 by 3, it would look like this. Zero equals 0 at the very bottom. That's because we have any value for z, because we can't find a value for z using RREF. So to simplify this, we can have let z equal t. Thus, our solution is going to be x equals -4 minus 7t, and then y equals 5. No, it should be -4 plus 7t. And then for this one, it's going to be 5 minus 5t. And then our z equals t, of course. So we can show our solution like this. We're allowed to do that. Don't worry about it. That's our solution. Because there's any value for z, and given that our x and y's could have different values depending on what value we have for z. Okay, so this one is a normal matrix, so we can convert that because it has 3 columns and 3 rows for variables and equations. So that shouldn't be very difficult when converting to a matrix. So from that, we're going to have, let's see, 1, 2, 3, -1, 3, 7, and then 1, -1, -3 equals 2, 4, 5. So how do we solve the system? To do this, we just do RREF again. So I'll let you guys do that. So you have, from the RREF, we have 1, 0, 2/5, 0. Then we have 0, 1, -3/5, 0. Then we have 0, 0, 0, 1. Now, you know from this that if 0 cannot equal 1, therefore, no solutions. Because there will be no value that can satisfy any of the equations because 0 cannot equal 1. So now let's look at this guy. One sec, let me just see. Yeah, okay. Just solve this using RREF again. So first convert to the matrix. 1, 2, 3. -1, 3, 7. And then 1, -1, 3, 2, 4, 6. So I see a similarity between that one. The bottom row is different from that bottom row, but everything else is the same. So I don't know, maybe this will get us an answer. Actually, wait. Both of those are the same. The very bottom right number is different by 1. So we'll see if that gets us anything, right? Maybe this will give us an answer. So doing the same RREF. So I forgot to put a -3 right there. We now have (1, 0, 2/5 equal to 0, 1, -3/5, 0, 0, 0, 0, 0. So now we have infinite solutions. So we don't even have to convert to a system. I can just say let z equal t. Therefore, we have the system x equals 2. Let's make this a little nicer looking. So to do that, all we have to do is multiply z by 5. So z equals 5t. We can do this because z can be anything we want. So if z equals 5t, then the fraction is gone. So x equals 2 minus 2z. Y equals 3z. And z equals 5t. So since z equals 5t, sorry, I forgot to make this t, not z, guys, t. So this is our answer. This is our solution. So next thing, convert to matrix, sorry, not equation. 1, 2, 3, -1, -2, -3. Then we have 1, 2, 3, 2, 4, 6. Now, what do you notice about all these equations? Well, they're all the same. This equals 2 times this, and this equals 3 times this. So if all the equations are multiples of each other, then that means there will be infinitely many solutions. Thus, since these can all be eliminated by this row, since they're multiples of each other, the RREF is something we can write down ourselves. You can put this into a calculator if you want. It will give you the same thing. So 1, -1, 1, 2, 0, 0, 0, 0, 0, 0, 0, 0. That's our answer. We have infinitely many solutions, and we can actually have 2 variables equal parameters. So let's let z equal lambda, and let's let y equal mu, because I like Greek characters. So turning that into a system, we now have x equals 2 plus mu minus lambda. Then we have y equals mu and z equals lambda. That is our answer. That's a fun little thing. So now we have k. We have a variable, we have a parameter here. So we can still do the RREF. So all we have to do is convert to matrix. So 2, 1, 2, -1, -2, -7, 3, -4, -19. Oh, that's an ugly number. Equals -1, 1, k. So the RREF of this will be, gotta plug this in. Actually, I changed my mind. I think it's better that instead of doing RREF, we can simply do our own row reduction, because this will teach us some important stuff with these matrix stuff. So let's do the thing that we've always been doing. So let's eliminate this part here. Get it to equal 0. So let's start with the 2. So row 3 minus row 1. And while we're at it, how about we do some multitasking? We can also do row 2 times row 2 minus row 1. So we're doing multiple things at the same time. And we're allowed to do that as well. That just speeds things up. So the first row doesn't change, of course. So 2, -1, 3, -1. Second row changes because 2 row 2 minus row 1. So 0, -4, so -3, -8, -11, 2 minus, so 3. Okay, so row 3 also changes, so 0, -6, and then -22. And then we have k plus 1. Okay. So now we can do some more stuff with this. And let's get the -6 to be 0. So to do that, we have to do row 3 minus 2 row 2. So to do that, the first row doesn't change. So 2, -1, 3, -1. Then we have 0, -3, -11, 3. That doesn't change either. This changes though. So 0, 0, also 0, k minus 5. So what can we do with this? Well, we can convert it back into a system real quick. So we have 2x minus y plus 3z equals -1. Then we have -3y minus 11z equals 3. Then we have 0 equals k minus 5. So if k is not equal to 5, then there's no solutions. Because if k equals not 5, let's say it equals 4, then 0 can't be -1, right? So it has to be 5. If k equals 5, infinitely many solutions. So let's just go up there, because there's more space up there. If we let k equals 5, then we have this. One sec. 2x minus y plus 3z equals -1. Then we have -3y minus 11z equals 3. And then 0 equals 0. Now, given that 0 equals 0, let's let z equal t. So if we let z equal t, that becomes, well, let's see now. X equals negative 1 over 2 plus 1 over 2y minus 3 over 2t. Then y equals negative 1 plus, actually, should be minus 11 over 3t. Then z equals t. That's our answer. So that's a bunch of more problems. And now we're going to move on to lines in 3D. Okay, so, one second here. Just going to get ready for this one. So that was a little bit of a review. You can read this later. I'll post the notes. But we looked over this a few lessons ago. Actually, one lesson ago. But yeah. So let's look at example 1. Use different vector notations to describe the displacement of a point that has moved 4 units right, 2 units into the page from the origin, and 5 units up. So this is our 3-dimensional Cartesian plane, and this is what it usually looks like. X is going in and out of the page. This is X. And Y is going to side, which is weird because that usually is X, right? But that's Y. Then Z is going up and down. So that's what it looks like. So if we have a vector that represents a point that moved 4 units right, that means it moved 4 units this way, 2 units into the page, so 2 units in, and then 5 units up. So that is our point. And this is our vector. So let's let our vector equal v. And v is equal to, let's start with a column vector. So that means if it moved 4 units right, then that's the y. If it moved 2 units into the page, then that's negative 2. Because x goes positive this way and negative that way. So negative 2, 4 units right, so that's 4, and then 5 units up, so that's 5. And another way to show this is using our algebraic vector, so 2i, negative 2i, plus 4, sorry about that, 4j, plus 5k. That's 2 ways to describe the vector. So what does the vector equation r equals this vector plus that times lambda represent? Well, it represents with the point 4, 2, 5 in the direction of 2, negative 1, 1. That's what it represents. Now, if we want to show this in Cartesian equations, it would be x, y, z equals, we're going to start by doing this. So 4 plus 2 lambda, 2 minus lambda, and 5 plus lambda. So if we go to a system, that would be x equals 4 plus 2 lambda, y equals 2 minus lambda, and z equals 5 plus lambda. So if we want to convert this into Cartesian form, we're going to solve for lambda on each thing. So lambda on the top is equal to x minus 4 over 2. Lambda in the middle is equal to 2 minus y. And lambda at the bottom equals to z minus 5. So Cartesian form is going to be x minus 4 over 2 equals 2 minus y equals z minus 5. That's how you do it. That's how you represent the Cartesian. Okay, next question. Example 3. Points A and B have coordinates A and B respectively. Determine a vector equation for the line AB. So, if we draw our little Cartesian plane, x, y, z, we have point A, which is 5, 3. This is point A. And this is B. Let's see. -2, 9. Okay, so this is B. And since both lie on this line, what we want to do is we want to convert it to this form. So R equals P plus lambda D. So D is our direction, and P is any point that lies on the line. So we can let P equal the position vector for A. So that's -5, 3, 4. And for D, D is just the direction. And when we subtract B from A or A from B, that represents the direction. So the direction could equal A minus B, which equals -5, 3, 4 minus -2, 9, 1, which equals to -3, -6, 3. So a direction vector is simply the direction and can be simplified to its lowest term. So we're going to simplify this. So it's going to be, we're going to divide everything by -3. So 1, 2, -1. So that's our D. So therefore, our vector equation is going to be -5, 3, 4. That's our position vector, plus lambda times 1, 2, -1, because that's the direction. So that's our vector equation, and our reminder is that lambda is an element of the real numbers. Okay, moving on. Determine a point of intersection between the lines R1 and R2. So in order to do this, we have to equate the two to each other. So we want to determine the point of intersection. We have to equate the two. So 7, 0, 5 plus lambda -1, 3, 2 equals 1, 6, 5 plus mu 4 over 4. All right, so how about we simplify this guy? So we're going to move all of the position vectors to the right and all of the parameters to the left. So now we have lambda times -1 432 minus mu times 404. That equals 165 minus 705. So if we simplify everything, we have negative lambda minus 4 mu, 3 lambda. One sec, guys. Three lambda, because there's no mu, and then 2 lambda minus 4 mu. And that all equals negative 6, 6, 0. So, what else is this? This is a system of equations. So, we can turn this into a system of equations, which gives us, we can actually turn it into a matrix, which gives us negative 1, negative 4, 3, 0, 2, negative 4, negative 6, 6, 0. That's our matrix. It looks kind of odd because there's more than one thing, but we can solve this pretty easily without even using RREF. So from here, we know that lambda equals 2 because 2 times 3 is 6. And if we plug it into here, into this equation, so negative 2 minus 4 mu equals negative 6. So that's going to be mu equals 1. Yeah. Okay. So given those, we can plug both into this equation here to make sure that it works. So plug it into this row here because we haven't used it yet. So 2, 2 minus 4, 1 equals 0. Well, 0 equals 0. So it's verified. It does intersect. Okay, so now we want to show that these lines do not intersect. Well, we're going to use the same exact method as we did before. We're going to do it a little differently just to show different versions. So for R1, we have X, Y, Z. Let me just like make this, instead of using matrices, we can be like X, Y, Z. X equals 1 plus. So R, if we look at R1 this way, 1 plus 2 lambda, 4 minus 3 lambda, and negative 2 plus lambda. And then R2, that gives us X equals 4 minus mu, Y equals 2 plus 4 mu, Z equals 4 plus 5 mu. So now what we're gonna do is we're gonna equate them to each other. So therefore we get one plus 2 lambda equals 4 minus mu, 4 minus 3 lambda equals 2 plus 4 mu, and finally negative 2 plus lambda equals 4 plus 5 mu. Okay, so now we're going to simplify this and we're going to turn it to this. So let's see. 2 lambda plus mu equals 3. Negative 3 lambda minus 4 mu equals negative 2. And finally, lambda minus 5 mu equals 6. Okay. So we're going to solve the top two, and then we're going to plug it into the bottom to see if it works. So we're going to use substitution here. So let's see. Actually, no, we can really just use elimination. So if we do 4r1 plus r2, that gives us this. So we're going to do it to the top. So 8 minus 3 is 5. Plus, okay, so equals 12 minus, so 10. And from that, lambda equals 2. And then plugging it into this equation, we have negative 4 mu equals 4, and then mu equals negative 1. So what happens if we plug both of those values into here? Well, that gives us 2 minus 5 times negative 1 equals 6. And that gives us 2 plus 5. So 7 is not equal to 6. Therefore, no solutions. Therefore, they don't intersect. They're skew. Okay. I'm going to let you guys do question 6 for homework. And once you're done, I want you to send the answers to me. Okay. And yeah, that is everything. That is our session. So, thank you guys so much for watching this. I'm really sorry about the technical difficulties I've been having lately. But yeah, we looked at systems of equations using algebra and technology. Then we looked at 3D vector equations and how those work. And yeah, so I will see you guys next session, and be sure to send the homework answers to me, and I will post these notes on the channel. Anyways, thanks so much for